Hello everyone, it's a pleasure to study the concept of proportional sequences with you all today. In the previous study, we learned that the characteristic of an arithmetic sequence is that starting from the second term, the difference between each term and its preceding term is equal to the same constant. What other sequences do you think are worth studying from the perspective of arithmetic, based on the research ideas and methods of analogical arithmetic sequences? Please observe the sequence in the following questions. The following sequences were recorded on the clay tablets excavated from the ancient Babylonian period in the 1 or 2 river basins, which we call Sequence 1, Sequence 2, and Sequence 3, respectively. Zhuangzi mentioned in the Book of Tianxia that a 1-foot-long stick can cut half of it every day, but it can never be cut off completely. It vividly illustrates the infinite separability of things. From a mathematical perspective, if we consider the length of a 1-foot wooden stick as a unit of 1. So from the first day onwards, the lengths of the wooden sticks obtained on each day are 1/2, 1/4, 1/8, 1/16, 1/32, and so on. 3. In the absence of limitations on nutrition and living space, a certain bacterium reproduces through division every 20 minutes, and each bacterium splits into 2. Therefore, the number of offspring produced by this bacterium from the first division is 2, 4, 8, 16, 32, 64, etc. We call this sequence 5. 4. Someone deposits a yuan in the bank for a period of 5 years with an annual interest rate of R. So, according to compound interest, what are the principal and interest he receives at the end of each year within 5 years? Compound interest refers to adding the interest and principal of the previous period together as principal, and then calculating the interest of the next period. So if we deposit a yuan at the end of the first year, we will multiply the principal a yuan by the interest rate R to get the interest plus the principal. So the sum of principal and interest is 1 times a plus R yuan. At the end of the second year, taking 1 times a plus R as the principal, and then multiplying it by the interest rate plus the principal, the sum of principal and interest can be calculated as 1 times a plus R square yuan. By analogy, we can derive the sum of principal and interest at the end of the third, fourth, and fifth years, and the sequence they form is called Sequence 6. What kind of operations do you think can be used to discover the patterns of arithmetic sequences by analogy? What patterns have you discovered again? We know that addition and multiplication are 2 basic operations in mathematics, and many variations follow the rules of addition and multiplication. We often refer to them as linear variations or exponential variations. We can observe these sequences and explore their value patterns through the inverse operation of multiplication and division. Let's first take a look at Sequence 1. If a n is used to represent Sequence 1, then we have a 2 equal to 9 compared to a 1, a 3 equal to 9 compared to a 2, and a 10 equal to 9 compared to a 9. This indicates that Sequence 1 follows a value pattern where, starting from the second term, the ratio of each term to its preceding term is equal to 9. The other sequences also have this pattern of values. Please describe the corresponding rules. Yes, starting from the second term, the ratio of each term to its preceding term in these sequences is equal to the same constant. Can you abstract the concept of an arithmetic sequence from the patterns of the aforementioned sequences, similar to the concept of arithmetic sequences? Let's first recall the concept of arithmetic difference. Generally, if a sequence starts from the second term and the difference between each term and its preceding term is equal to the same constant, then the sequence is called an arithmetic sequence. This constant is called the tolerance of an arithmetic sequence. We usually use the lowercase letter to represent tolerances. What about analogical sequences? How do we define it? Generally, if a sequence starts from the second term and the ratio of each term to its preceding term is equal to the same constant, then we call this sequence an arithmetic sequence. This constant is called the common ratio of an arithmetic sequence, usually represented by the lowercase letter q. How to express the above definition using algebraic method? We can express the arithmetic sequence as a n plus 1 minus a n equals d. Among them, n belongs to n stars. The tolerance d can be positive, negative, or 0. What about geometric sequences? We can express it as a n plus 1, a n equals q, and n belongs to n star. What is the range of values for common ratio q? Let's explore through the following exercises. Determine whether the following sequence is an arithmetic sequence based on its definition, and if so, write its common ratio. Let's first take a look at Sequence 1. From observation, we can know that if the sequence is set to a n, then adding 1 to a n equals 1.1, so it is an arithmetic sequence with a common ratio q of 1.1. Let's take another look at sequence 2. If we set this sequence as bn, we will find that b2 is greater than b1. It is meaningless, so it is not an arithmetic sequence. From this, we know that the first term of an arithmetic sequence cannot be 0, so can the common ratio q be 0? If we remove the first term of this sequence, do the following three numbers form an arithmetic sequence? We see that at this point, b2 is equal to 0 compared to b1, but because b2 is equal to 0 and b3 is meaningless compared to b2, it is not an arithmetic sequence. Then we know that the ratio q cannot be 0. Let's take a look at sequence 3 again. If we set the sequence to Cn, we observe that Cn plus 1 divided by Cn equals -2. So it is an arithmetic sequence where the common ratio q is -2. From this, we know that the common ratio can be negative. Let's take a look at sequence 4 again. If we set this sequence as dn, then dn plus 1 is equal to dn, so the common ratio q of an arithmetic sequence is equal to 1. By recalling it again, we can summarize it. A non-zero constant sequence is both an arithmetic sequence with a tolerance of 0 and an arithmetic sequence with a common ratio of 1. Through the above exercise, we can summarize that the range of values for the common ratio q can be positive or negative, but not 0. In arithmetic sequences, we have learned the concept of terms in arithmetic. By analogy, what corresponding concepts do we have in arithmetic sequences, and how do we define them? Let's first recall the simplest arithmetic sequence consisting of three numbers, a, upper letter a, and b, in which is called the arithmetic mean of a and b. According to the definition of arithmetic sequences, 2a is equal to a plus b. So what about arithmetic sequences? The simplest arithmetic sequence consisting of three numbers a, g, and b is called the arithmetic term of a and b. According to the definition of an arithmetic sequence, we know that g is equal to a and b is equal to g. Therefore, we can deduce that the square of g is equal to a multiplied by b. Can you derive its general formula based on the definition of an arithmetic sequence? Recall the derivation process of the general term formula for arithmetic sequences, analogical conjecture, and how to derive the general term formula for arithmetic sequences. Let's first review and recall the derivation process of the general term formula for arithmetic sequences. Because a 2 is equal to a 1 plus d, a 3 is equal to a 2 plus d, we substitute a 3 equal to a 1 plus to d. A 4 is derived to be equal to a 1 plus 3d. Through induction, we can obtain that a n is equal to a 1 plus n minus 1 times d, where n is greater than or equal to 2. When n equals 1, we can prove that the above equation also holds. Therefore, the first term is an arithmetic sequence with a tolerance of d for a 1, and the general formula for a n is that a n is equal to a 1 plus n minus 1 times d. So, analogous to in geometric sequence, we can know from the definition of a geometric sequence that a 2 is equal to a 1 multiplied by q. A 3 is equal to a 2 multiplied by q. By substituting a 2 as a 1 multiplied by q, we can organize it into a 1 multiplied by q squared. Similarly, a 4 can be obtained as a 1 multiplied by the third power of q. We can observe the relationship between the number of terms and the exponent of the common ratio q. A n is equal to the product of a 1 multiplied by q minus 1 to the power of n, which is greater than or equal to 2. Also, because a 1 is equal to a 1 multiplied by the 0 power of q, and 0 can be understood as 1 minus 1. That is to say, when n is equal to 1, the above equation also holds. Therefore, if the first term is an arithmetic sequence with a common ratio of q to a 1, the general formula for a n is that a n is equal to a 1 multiplied by q to the power of n minus 1. The above reasoning process belongs to inductive reasoning, and the conclusion obtained from inductive reasoning is only a conjecture. Later, we can use mathematical induction to provide a rigorous proof that the above general formula is correct. Besides induction, what other methods have we used to derive the general formula for arithmetic sequences? Yes, we also used the accumulation method. Then what method can we use to derive the formula for the general term of an arithmetic sequence from the perspective of operation using the analogy thinking method? Yes, we are considering using cumulative multiplication. First, let's recall the method of using cumulative addition to derive the general formula for arithmetic sequences. From a 2 minus a 1 equals .3 minus a 2 equals d to a n minus 1 equals d. By adding the left and right sides of the above equation in sequence, n minus a 1 equals n minus 1 times d, so n is equal to a 1 plus n minus 1 times d. Analogous to geometric sequences? We go from a 2 to a 1 being equal to q, a 3 to a 2 being equal to q, until a n is equal to a n minus 1, which equals q. We multiply the left and right sides of the above equation in sequence, and we find that a 2, a 3, a 4 to a n minus 1 numerator all approximate the denominators. On the right side of the equal sign is n minus 1 q. Therefore, it can be obtained. The ratio of a n to a 1 is equal to q, where n is subtracted by 1 power. We have derived that a n is equal to a 1 multiplied by the n minus 1 power of q, so we can also derive the general formula for arithmetic sequences using cumulative multiplication. In an arithmetic sequences with a tolerance d not equal to 0 can be associated with the corresponding linear function. So for an arithmetic sequence, what conditions can a sequence with a common ratio q satisfy to establish a similar relationship with the corresponding function? Let's first take a look at the general formula for geometric sequences. A n is equal to a 1 multiplied by the n minus 1 power of q, and we find that it can be written as a 1 divided by q multiplied the n power of q. So when q is greater than 0 and q is not equal to 1, the nth term a n of the proportional sequence a n is the exponential function fx, which is the value of the function when x equals n. Let's use the function graph to understand that when q is greater than 1 and a 1 is greater than 0, we know that the exponential function fx graph is this monotonically increasing curve, and the image of the sequence is the point on the curve where the horizontal axis is a positive integer. On the contrary, for any given exponential function fx equal to k times the power of a, we can know that f1 is equal to ka, f2 is equal to ka square, and fn is equal to k times the n time power of a. So it forms a geometric sequence k to the n time power of a, with the first term being ka and the common ratio being a. From this, we conclude that geometric sequences with a common ratio q greater than 0 but not equal to 1 can be linked to the corresponding exponential function. Can you explain the monotonicity of a geometric sequence with a common ratio q greater than 0, similar to the properties of exponential functions? We observe the analytical expression of exponential functions from a functional perspective and find that its monotonicity is not only related to the range of q values, but also to the sign of a 1. Therefore, we can gradually summarize it as follows. Let's first look at the exponential function y equal to the power x of q. When the base q is greater than 0 and less than 1, it monotonically decreases, and when q is greater than 1, it monotonically increases. The base q of an exponential function cannot be equal to 1. Let's take another look at the monotonicity of the proportional sequence a n equal to the nth power of q. We can easily conclude that its monotonicity is consistent with the monotonicity of the exponential function mentioned above. The common ratio q of an arithmetic sequence is equal to 1. At this point, a n is equal to 1 and is a constant column, so its monotonicity remains unchanged. Let's take a look at the arithmetic sequence again. A n is equal to the product of a 1 and q minus the power of n. Therefore, its monotonicity is related to both the range of q values and the sign of a 1. When a 1 is greater than 0, we can easily obtain its monotonicity consistent with the above monotonicity. When a 1 is less than 0, monotonic decrease becomes monotonic increase becomes monotonic decrease. Next, let's apply knowledge to solve problems. If the fourth and sixth terms of the proportional sequence n are 48 and 12, respectively, find the fifth term of the sequence n. What are the values of the quantities that determine the general formula for proportional sequences? Yes, determined by the first item a1 and the common ratio q. So, we can obtain two sets of equations about a1 and q using the general formula for proportional sequences from the known a4 and a6. Divide the two sides of equation 2 by the two sides of equation 1, and the solution is q squared, which is equal to 1/4. So q is equal to plus or minus 1/2. We first substitute q equal to plus 1/2 into equation 1, and we can obtain a 1 equal to 384. At this point, using the general formula of a 5, which is equal to a 1 multiplied by q to the 4th power, substitute the value into the calculation to obtain 24. Similarly, by substituting q equal to -1/2 into equation 1, we obtain a 1 equal to -384. At this point, a 5 is calculated to be equal to -24. Therefore, the fifth term of the sequence n is positive or -24. So we found that given two independent conditions, we can find the formula for the general term of an arithmetic sequence, and thus solve for a certain term of the sequence. Let's observe again, what is the connection between the requested a 5 and a 4, a 6? Yes, a 5 is the proportional median of a 4 and a 6. So we can use the concept of the term in proportionality to derive that the square of a 5 is equal to a 4 multiplied by a 6, which equals 576. Therefore, a 5 is equal to plus or minus the square root, and 576 is equal to plus or minus 24. We clearly feel that the concept of proportional terms has greatly simplified our calculation process. So when solving mathematical problems, we hope that everyone carefully observes the conditions of the problem, combines existing knowledge, and chooses the most convenient solution method. Example 2 is known that the common ratio of an arithmetic sequence n is q, and the nth term n is represented by the mth term am of n. Based on the experience of the previous question, we can still use the general formula for proportional sequences to write the equations for am and n with respect to a 1 and q. By dividing the two sides of equation 2 by the two sides of equation 1, we can obtain that a n is equal to q to the power of n minus m. So, n is equal to am multiplied by q to the power of n minus m. Any term of an arithmetic sequence can be represented by a certain term of the sequence and a common ratio. So, is there a similar conclusion for arithmetic sequences compared to arithmetic sequences? We can also write two equations for am and a n with respect to a 1 and tolerance d using the general formula for arithmetic sequences. Subtracting the two sides of 1 from the two sides of equation 2 yields a n minus am, which is equal to n minus m times d. Therefore, a n is equal to am plus n minus m times d. So any term of an arithmetic sequence can be represented by one of its terms and a tolerance or common ratio. Let's reminisce about this lesson together. We derived the concept of arithmetic sequence from the concept of arithmetic sequence by analogy, and the range of values for the common ratio q, as well as the general formula and variations of the general formula for arithmetic sequences. We have found that analogical thinking is a link between old and new knowledge, and an important source of mathematical development. Many theorems, formulas, and rules in mathematics are proposed through analogical reasoning. Analogy is one of the most fundamental and important mathematical thinking methods. It not only solves the unknown from the known and complex problems from simple problems, but also embodies the wonders of mathematical thinking. The appropriate use of analogical thinking can help people draw analogies and improve their problem-solving abilities, as well as guide them to explore and acquire new knowledge, enhancing their innovative thinking skills. That's all for today's class. Goodbye.